A very warm welcome to the class, children. So today's topic is study of sound part 1. What do you observe in these images? Yes, that the people are enjoying the music. In this image you can see they are enjoying with the help of radio, and here you can see the people are enjoying the music by wearing nice headphones. Now how does this sound reach their ears and they are able to enjoy is what we are going to study in this chapter. Okay? Just a quick recap about what we had done in the standard 8, that they say sound wave requires a medium. When I say a medium, that means it can be either solid, liquid or gases. It requires a medium that so that it reaches the ears. If you recall the previous image which I had shown you all, the loudspeaker or the radio was just kept it at a particular distance or near a person's shoulder, but the other person who was far away also could hear the sound. That means the sound wave or the sound could travel through the medium, and the medium in that case was gases, that is air. Okay, but it does not happen in all the mediums. There are certain medium, that is the vacuum, does not let the sound wave travel through it. For that we had explained an experiment which was done in the class 8, that check out this first jar wherein a bell is attached to it and there is air present in the jar. We could easily hear the sound of the bell, but in the second jar, gradually through a particular pipe, the air was removed, so less sound was heard. And in the third jar, totally the air was removed from the bell jar. So that means when totally the air is removed from the bell jar, it is nothing but it has now vacuum inside it. This third bell jar has vacuum inside it, and now we could not hear any sound, so no sound was heard. So this means that the sound wave requires a medium, but it does not pass through or is not able to be heard when there is vacuum. Okay, so this was a quick recap of what we say, that a medium is necessary for the propagation of sound waves. It is said that sound is a wave as well as a form of energy. Now this can be clearly shown by this diagram, which shows that these particles are moving and dashing each other. So while they are moving, this first ball is initially in the potential energy state. Then when it is moving, it is making it into the kinetic energy state. So that is why there is a transfer of energy taking place. So it is called as a form of energy. And why it is called as a wave? As what is a wave? Wave is a continuous disturbance. Again, as this diagram shows, there is a continuous disturbance which is occurring in these particles. That is why it is called as a wave. So understood, children, why sound is a wave as well as a form of energy? There is a transfer of energy, that is initially the particles are in the potential energy state, and because they are moving, they again go back into the kinetic energy and again in the potential energy state. So that is why they are called as a form of energy. Sound is waves are called as a form of energy. And why they are called as waves? Because there is a continuous disturbance which keeps on occurring in the particles, and a wave like pattern occurs. There are types of waves. There are rather two types of waves, I would say, the mechanical waves and the electromagnetic waves. The mechanical waves, they require a medium, whereas the electromagnetic waves, they do not require a medium. The mechanical waves are of again two types, longitudinal waves and transverse waves. Longitudinal waves, examples are the sound waves which we are going to study, and transverse waves, the examples are the water waves. In electromagnetic waves, we have light, microwave, infrared, X-rays, ultraviolet rays and radio waves. So we are not going to study about the electromagnetic waves in this chapter, but we are going to study about these two waves, that is longitudinal waves and transverse waves. So what are longitudinal waves? As this GIF of this longitudinal wave shows, when a spring is being pushed, initially it comprises together and again comes back to its original position. So that means there is an energy transport which takes place from the left to the right. But you can see that initially they are coming together and again coming back to their original position. That is, they are becoming straight. That means there is some kind of a to and fro, which in terms it is called as oscillation. So there is the particles of the medium, they oscillate about their central or the mean positions, and it is parallel. The propagation is parallel to the waves. Okay, the propagation is parallel. So such kind of waves are called as longitudinal waves. When the energy transport is taking place from left to right and the particles of the medium, they oscillate about their mean positions, which is direction parallel to the propagation of the wave. So such waves, they are called as longitudinal waves. So when the spring was coming together, that thing is called as compression, which is nothing but the place of, can say, higher density. Okay, the place of higher density. When the spring was spread enough, that means it was the place of low density. So that part is called as rarefaction. Again it was a compression, again it was a rarefaction. Okay, this is how the longitudinal wave occurs, which is, we said, it was parallel to the propagation of the wave. The medium, that is the particles which were moving, they were in the direction parallel to the propagation of the wave. So you understood what is compression and rarefaction. When this is the place of higher density, when all the particles were together. Okay, that is compression. And when the particles again were moving apart, that becomes a rarefaction. That is the place of lower density. Then what is a transverse wave? Transverse wave, we can see that these particles of the medium, they oscillate up and down. They oscillate up and down. Can you see? They are oscillating up and down. Such oscillations, they are perpendicular. Okay, if I have to draw a graph like this, and if this is the mean position, you can see the direction of the propagation of the wave is perpendicular. Okay, it is perpendicular. If I say this is, if I draw a graph here, it is perpendicular. So such waves are called as transverse waves. When the oscillations are perpendicular to the direction of the propagation of the wave, such waves, they are called as transverse waves. Okay, the oscillation is up and down, whereas in the longitudinal waves, the oscillation was about its mean position. That is, that oscillation means to and fro, so it was coming back and forth to the same position like a swing. Just a difference between the longitudinal wave and the transverse wave. The longitudinal waves are those waves in which the particles of the medium move parallel to the propagation of the wave. Okay, and transverse waves are those waves in which the particles of the medium move perpendicular to the direction of the propagation of the wave. I'll just underline this, that this is parallel and this is perpendicular. For example of longitudinal waves, sound waves are longitudinal waves, whereas for example ripples formed on the surface of the water in a transverse wave. That is, when you drop a stone in water, how those waves are formed, no? So that is nothing but the transverse waves. I hope you have understood what is a longitudinal wave and what are the transverse waves. Then, as I had shown you all about the compression and the rarefaction, this is according to the change in density. When the loudspeaker is on, the particles start moving away from the loudspeaker. So this is, again, C indicates the compression. Okay, the C indicates the compression, whereas this R indicates the rarefaction. Okay, so in change in the density, so how, see, they are moving, oscillating in their mean position. So this is, initially it is together, all the particles are together, then they are far apart, again the particles are together, again they are far apart. So this is about in density. In case of the pressure, this is how it occurs. They are together, particles are together, again far apart. C represents, as I told you, compression, and R represents rarefaction. Then they are apart. Okay, so if you have to draw a graph regarding this is the average, that is the mean position. So initially the density would be high, and then it would go low, then again high, then again low, then again high, then again low. This is how it occurs. So when it is high, this part is known as the crest, whereas the lower part is known as the trough. This you have to remember. Okay, so this is the mean position, and this is how the waves, this is how the graph looks like. The density initially is higher, then the pressure becomes lower, then the higher, then lower, and this is how it occurs. Okay, then what are the characteristics of the sound waves? The first characteristic is the wavelength. Now what is a wavelength? The wavelength is nothing but it is this distance between the crest. Okay, it is the distance between the crest. It's called as the wavelength, and it is denoted or indicated by the Greek letter. It is denoted by the Greek letter lambda. Okay, so understood what is a wavelength? The wavelength of this of a sound wave is the distance between these two crests. Okay, it is the distance between these two crests. This was the first characteristics of the sound wave. The second characteristics of the sound wave is the frequency. Now, as the literal name of the meaning of the frequency says that, if I have to tell you all that down near my Nagar bus stop, for example, I have to give you all this 33 bus, in an hour it comes 3 times. In an hour it comes 3 times. That means the frequency of that bus in an hour is 3. Understood what is frequency? You say na, this person frequently visits my place, or this I frequently go to this restaurant. So that is number of times how much you are visiting anyone's place or any other restaurant. So that is known as the frequency. So that is the second characteristic of the sound wave, that is indicated by nu, and it is written as this. Okay, nu, this is known as nu. So this is low frequency. Can you see how it is? The wavelength is more, so low frequency. This is medium frequency, and the wavelength is less, so it is high frequency. Okay, more wavelength, then low frequency, and accordingly then the wavelength becomes less, then high frequency. Understood? So the wavelength has to be less for the frequency to occur more, and is denoted by the by nu. The third characteristic of the sound wave is the amplitude. Now what is an amplitude? It is a maximum value of the pressure or density. Now we have seen the graph. So if I have to draw here, okay, density or pressure. So whichever is maximum, that is called as the density. That is called as the amplitude. So this is called the amplitude. If we have to count the trough, or we have to count the pressure, that is the amplitude. Again, in this case, this is the amplitude. Here, this is the amplitude, and here, this is the amplitude. So what do we define amplitude as? It is the maximum value of pressure or density. It is the maximum value of pressure or density. Okay, and it is indicated by A. Understood what is amplitude? It is the maximum value of pressure or density. The next characteristic of sound wave is the time period. So the time taken for one oscillation of pressure or density at a point in the medium is called the time period. That is from here till here. Okay, how much time it takes for that oscillation to occur, it is called as a time period. Then the next time period would be from here till here. Okay, so I would write here, what is the time period? It is the time taken for one oscillation of pressure or density at a point in the medium. At a point in the medium is called the time period, and it is denoted by T. Okay, in this case, as I said, this would be the time period for the another oscillation to occur. The next characteristic of the sound wave is the pitch. Now this is determined by the value of frequency, whether it would be higher or lower. So low frequency, low pitch. For example, they have given us of this. This is an example. This is the wavelength. Remember, this is the wavelength. Here, longer the wavelength, longer the wavelength, low would be the frequency, and if low frequency, then it would be lower pitch. Similarly, the wavelength here is shorter, that is why high frequency, then high frequency, that is why high pitch. If I have to give you an example, I will give you an example of a crying baby. The frequency of the sound of a crying baby is more, isn't it, than that of the crying adult. So the sound of that crying baby is more shriller. Shriller means it is more piercing, isn't it? It is more piercing than the crying of the adult. Similarly, the voice of the female is more shriller, that is, it is at more higher pitch as compared to the male. So that is why when they shout, it is a kind of piercing sound which is there into your ears. Okay, so that is why we can make out whether it is a male voice or whether it is a female voice. All these musical instruments, they work on this principle of high pitch and low pitch. If I have to give you an example of the musical instruments, like this flute, the pitch of the sound changes continuously by changing that they have the holes on it, no? So they keep on placing their fingers over those holes, so that different pitches of sound keeps on coming. So when the different holes are being placed, fingers are placed on these different holes, they closed at one point, and the voice accordingly comes out. Even in the stringed instruments, that is your guitar and all this, there are different the thickness of the strings are different, so accordingly they are been plucked. Okay, plucked, not to totally removed out, accordingly they are being plucked so that it gives a different sound. So whistle gives a high pitch sound and drum gives a low pitch sound, because this is little irritating, isn't it? These high pitch sounds are little irritating as compared to the low pitch sounds. Then the next characteristic of the sound wave is the amplitude. Now what is the amplitude? The amplitude determines the strength or the loudness of a particular voice or a particular sound. So high amplitude, the sound will be loud. If the low amplitude, then sound will be quiet. Remember, what is amplitude? It is the maximum value of pressure or density. Remember, no? It is a maximum value of pressure or density. So this is your amplitude. So your amplitude is high, the sound would be loud. Here the amplitude is low, the sound would be quiet. Okay, understood? What is amplitude? These are just some examples of soft and the loud sounds. Okay, a girl playing quietly is a soft sound. A girl and a boy who are using their musical instruments to create some music, but that becomes really loud. The snake hissing is a soft sound. The bike coming with its noise, that is again a loud sound. The fire engine or the ambulance again making noise, that is a loud sound. But a snail, a person sleeping, a butterfly again becomes a soft sound. A parrot chirping very loudly, again that is a loud sound. Next we need to study about the velocity of sound. So there is a small activity which says take your friend to a place where there are iron pipes, example the school veranda, staircase or a fence. Stand near one end of the pipe and ask the friend to stand 20 to 25 feet away from you near the pipe. Okay. Ask the friend to gently tap the pipe with a stone. Press your ear to the pipe and listen to the sound coming through the pipe. The same sound coming through the air can also be heard, but which sound reaches you first? So even though you can hear the sound of that tap with a stone from both through the iron pipe as well as through the air, but from this activity you can see that you hear the sound through the iron pipe much before you hear it. Okay, you hear it from much before through the iron pipe than through the air. So this shows that this shows that sound travels faster in the iron than in air. So more specifically, if I have to say that the sound travels faster in solids as compared to the gases. Okay, sound travels faster in solids as compared to gases. Now how do we measure this velocity of so how do we calculate the velocity of sound? So the distance covered by a point on the wave, whether it is at the point of higher density or lower density, in unit time. So how much distance it is covering in the unit time is the velocity of the sound wave. So velocity is equal to distance upon time, but at any point on the sound wave we have taken the distance as lambda. So distance is equal to lambda, that is your wavelength, and in time, that is t, that is your time period. Okay, so this can be written as velocity of sound is equal to wavelength upon time period, that is v is equal to lambda upon t, but 1 upon t is equal to nu, which means that this is time period and this is frequency. Okay, this is frequency. So they are inversely proportional to each other. When the time period increases, the frequency decreases. The time period decreases, the frequency increases. That is why it has been written as 1 upon t is equal to nu. So we can substitute this 1 upon t is equal to nu here. So this means v is equal to lambda into 1 upon t. So this 1 upon t can be replaced with nu. Nu, that is v is equal to lambda nu. So which means that your velocity of sound is equal to wavelength multiplied by frequency. Okay, this is your formula. Velocity of sound is equal to wavelength into frequency. As we had studied in the previous activity which we had done, that we could hear the sound of that stone which was hit through the iron pipe. We could hear it through the iron pipe much before you could hear it through the air. So this is just a table which they have given that shows velocity of sound in various mediums at 25 degrees Celsius. So in case of solid state aluminum, it is 5420 meter per second, it travels so faster, whereas in liquid you can see it is 1531. In gases it is 1284. So if you see or compare the solid, liquids and gases, we can see the sound travels highest in the solids. So in any medium at fixed physical conditions, the velocity of sound of different frequencies is very nearly the same. The velocity is highest in the solids and least in gases. It increases with an increase in the temperature of the medium. So whenever there is an increase in the temperature, the velocity of the sound wave would increase. So this Italian physicist Borelli and Viviani in the 1660s first calculated the speed of the sound. They measured the time between seeing the flash of a gun and then hearing it sound from a long distance. Their value of 350 meter per second is very close to the value of 346 meter per second, which we accepted today, which we still accept today. The same goes that during the lightning which strikes, we see the lightning first and then we get to hear the thunder, because the light waves travel much faster than the sound waves.